just a minute or two for everyone to file in. Great to see so many people with interest in this webinar. Hope everyone that's in that was managing the snowstorm yesterday and this morning has dug themselves out and wasn't too impacted. And we have a few folks that are joining us from overseas interested in this as well. So welcome. I guess good afternoon or good evening. Okay, great. So we'll let a few folks file in as they come. We'll move on with the topic of today, which is just a general overview of ground improvement here in Canada. We'll talk a little bit about who Menard Canada is, what sort of work we get up to, some of the ground improvement techniques that we're using. I've got a lot of project examples here today that try to highlight some of the advantages of using ground improvement techniques versus some traditional methods. If you don't know what ground improvement is yet, don't worry. We'll cover that as well, and then we'll get into some questions as well. So the questions are activated. Q&A session. Please put any questions you have in there, and our moderators will sort through those, and we'll probably have time for a couple of those at the end of the presentation. And anything that we don't get to, we will attempt to follow up with maybe some of the frequently asked questions from today's webinar once we're done here. So Menard Canada, who are we? What problems do we solve? So Menard is a design build ground improvement contractor, formerly Geopack here in Canada. So it was established in 1971. Geopack was the first licensed user of the Menard pressure meter here in Canada. So this was a technique that was invented by Menard's founder, Louis Menard, back in 1955, patented in 1955. I guess there's quite a bit of development and still has been. And this was a sort of a revolutionary way to better understand the in situ strength, stiffness properties of soil and allow us to treat them in ways that didn't require massive bulk excavation of what we deem to be poor soils or more costly deep foundation systems. So this instrumentation really opened up a lot of opportunity for techniques like you see on the right here, which is a dynamic compaction. We'll tell you what that is. That's an exciting project in Montreal, kind of from back in our history. And Menard Canada has pioneered a lot of geotechnical technologies here in Canada. So the pressure meter, of course, being brought in 1971. Dynamic compaction followed after that. Menard vacuum, which is a consolidation technique for dealing with soft soils. And then controlled modulus columns, which is when we start getting into concrete-based ground improvement methods, which was in the mid 1990s. Currently, Menard Canada has several offices. We're coast to coast. We are your ground improvement team, whether you're out in BC, whether you're in the East Coast or anywhere in between. Offices in Vancouver, Kelowna, Calgary, Hamilton, where we're presenting from today, Toronto, Ottawa, and Montreal, with great teams of folks here that are very approachable. If you guys have any questions after this, you'd like to talk with somebody who's more local, check out our website. There's contact details are there. Don't hesitate to reach out. You'll be in very good hands. So what type of jobs do we get involved in? So really, when it comes to ground improvement, we're focused on soil conditions. Soil conditions could be below buildings. We could be talking about poor soil conditions below roads, railways, industrial facilities. These could be even marine facilities, ports, airports. Really, there's the application is almost as wide as would be available. If you have poor soils, there's something that may be able to be done more effectively, and we'll get into how we manage that in a second. So when you're on these projects, how do you deal with this photo here, loose fill soils? This is a site we completed 2 years ago now. Photo before we started is old pit and quarry that have been backfilled over time with material from other construction sites, and now they're looking to repurpose that land, redevelopment. But obviously this represents a substantial amount of risk to the project. What if you have deep and compressible soils? So you don't need to be a geotechnical engineer, though I'm sure we have quite a number on the call today to understand this graph. What I'll tell you is that when you see red on a log like this, it's not good. And it usually means if you're the person that's trying to advance a project, you're going to spend a lot of time and a lot of money trying to deal with this if you don't come up with creative solutions. So before we get into the creative solutions, let's talk about some of the traditional techniques. So when you have challenging soils on your site, typically your recommendations are going to be to bulk excavate would be one option. So removing all that poor soil, replacing it with engineered fill. This is a technique that works well. It's been used a lot on a lot of projects, all over the world. But it does have some associated costs, associated challenges and risks with it. The first thing you can see in this photo, when you're trying to build, say, property line to property line, you may need to get into shoring systems to be able to remove all this poor soil. That's an additional cost of the project. You might have high groundwater conditions that force you into dewatering, again, adding kind of cost and complexity to the works. Now you're also adding the soil disposal, trucking, which not only congests the road, upsets the local communities, but it's also generating quite a lot of carbon emissions, which I know everyone is very focused on now, understanding how we can understand what our carbon emissions are, where we are now, and how we can get them to a level that's significantly lower than where they've been in the past. The other option that you're often presented with would be deep foundations. So whether this is a driven pile, maybe a helical pile, a drilled caissons, continuous flight augers. A lot of these methods, not all of them, but a lot of them will generate drill spoil. So you're still pulling up quite a lot of material out of the ground. That material needs to find a home. That's getting back into the trucking and the congestion. They also have higher material inputs in terms of steel, concrete, or grout. And then structurally, they're going to require things like pile caps, grade beams, structural slabs, which are more costly and take a little bit longer to execute on site than conventional foundations. So what do conventional foundations look like? So shallow foundations, as you can see in the back, pretty straightforward. Less excavation, fewer material inputs. So the idea being limit the amount of concrete, limit the amount of reinforcement that you need. Of course, these are going to be dependent on the existing ground conditions. These are faster and more economical to install than pile caps, grade beams, structural slabs, and they can be installed often by contractors that may not have the same level of sophistication as you might want to select for more complex piling type approaches. And then again, speaking of of the environmental impact, this is your lower impact option. If you can get away with high capacity strip and spread footings on your project, place that as high in elevation as possible, that's going to be the lowest impact to the environment. It's going to be the lowest impact to your project costs, and it's going to be the lowest impact to your project schedule. But could this be a reality? Could shallow foundations be a reality when you're dealing with challenging soils on site? And that's where ground improvement comes in. So let's take a bit of a step back now. We've sort of introduced the topic and talk a little bit more deeply. What is ground improvement? So this is it's a name that's used to describe a number of construction techniques that use mechanical means to improve poor soil conditions. You may be looking to improve the strength and stability of your site. Perhaps you have a concern about the total or differential settlement that would occur if you're going to place a new building on poor soils. Maybe it's a roadway embankment or a retaining wall, a new tank, for example, storage tank. You may also have concerns with loose soils having liquefaction potential, so seismic events causing challenges in terms of liquefaction settlements, and like we mentioned with retaining walls and embankments, making sure that the site has the stability to support those embankments without failures. And I think everyone probably has seen some examples in the world of some of these failures. The idea here is if you can manage the risk below what you're trying to put on using techniques like ground improvement techniques, you can save a lot of time, money, but you can also achieve what you're trying to do in terms of project performance and the long-term stability of these sites. Ground improvement also allows you to simplify your construction. So if you are going to significantly limit the amount of excess soil you're going to generate from either a bulk excavation or a drilled caisson, for example. That means less trucking off of your site. That means less coordination. And certainly here in Ontario, the new excess soil regulations, is very prescriptive of how you have to manage excess soil. So the less of it you can generate, the easier it is, and this also generally correlates directly with the economic impacts of the project as well. And then the bigger one I think is just limiting your overall risk. So anytime you're dealing with the ground, there's always inherent risk. There's no way to know 100% of everything that's existing, below a building, below a property. And if you can reinforce or strengthen or stiffen that, homogenize the site, make it all consistent, you reduce a lot of risk on your projects. And what that means is that when you go out to construct, you're not coming up with surprises that you need to manage, which are often more costly and have significant impacts to projects in terms of delays and again, economic factors. So there's a lot of different ground improvement techniques. We're not going to have time to cover them all today. Again, this is more of a general overview of some of the main techniques that are being used here in Canada. These methods can generally be broken down into reinforcement techniques, which is when you're adding some sort of material into the soil to improve the properties of that material. Densification techniques, which is using energy to change the nature of the soil, or consolidation and drainage techniques, which help on compressible sites when you have soft clays and you're adding new load and you're worried about long-term settlements. So we'll talk quickly at first about soil densification. And the idea here, as we mentioned, is to simply stabilize loose soils. So this could be viewed as your engineered fill or your bulk excavation, really without ever putting shovels in the ground. So instead of removing all this soil, putting it all back in lifts or bringing in import material, you can densify what's there in place, get to the same capacities, and save a lot of risk on the site. There's a number of different ways to do this, and we'll show a couple options really where the energy sort of increases as we go. What you see here first is a system called rapid impact compaction. So this is generally a 9-ton hydraulic hammer that can strike a 5-foot diameter tamper foot that's in contact with the ground, a rate about 40 times a minute, and that can treat loose fills, loose sands to a reasonable depth below that tamper foot. As the energy increases, you get into techniques like dynamic compaction, which we mentioned was one of the first techniques, ground improvement techniques, that was brought to Canada by Menard when we were formerly Geopack. And then vibro compaction. So again, going from excavator mounted equipment into medium-sized cranes to maybe larger sized cranes, and to manage different risks and different soil profiles. You can see here, I like this graph because it kind of gives a sort of an indication. We talked about the increase of energy, but what you can see is your typical roller compaction, or that heavy proof roll that you do on site, may densify the upper foot or 2 feet or so of the soil. Rapid impact compaction, for example, will extend that to maybe 5 or 6 meters in the right soil conditions. Dynamic compaction allows you to double that treatment depth down to maybe 12 meters or deeper. And then vibro compaction is really, if you've got soils deep enough and you've got a crane with enough cabling, you can get the job done. And our teams on the West Coast are doing a lot of vibro densification to manage liquefaction risk throughout BC. And a lot of their techniques are going down 20, 30 plus meters using vibro flots on cranes. So a quick example here. So this is an industrial warehouse. This one's in southwestern Ontario. This site again was a former gravel pit. I think maybe there's starting to see a bit of a trend in some of these former pits and quarries starting to be redeveloped and turned into some beneficial use, which is really great to see. I think there's a lot of awesome opportunity there. But this particular site had about 5 meters of fill that had been brought in, plus some weak soils that were below it. Dynamic compaction was used to densify the entire site, plus some new upfill that was required to bring it to the final site grades, and it avoided over 75,000 cubic meters of removals. So you think about the number of trucks that would be needed to haul this material off, or the number of equipment that would be required to manage the sorting and recompaction of this soil, versus placing a single crane out on the job site working for a couple of weeks to get the job done. We did a very detailed carbon emission analysis of this project using a third-party calculator available from the Deep Foundation Institute online. If folks can look that up if they're ever interested in knowing what the carbon emissions are of their projects. Maybe they're looking to compare piling solutions or dig and replace with some ground improvement options. This particular site had less than 1/10 of the carbon emissions of the proposed earthworks. And in fact, much of the carbon emissions that were generated were from the earthworks process to upfill the site prior to the compaction, which was calculated in that analysis. So this can be a big impact. This particular site we would estimate to be about 1/5 the cost as well as the earthworks operation. Another distribution warehouse, this one in Toronto, a very large warehouse. This again, an old dump site, only about 3 meters of poor soil. So we're getting into that sort of shallower depth, which allowed us to use a rapid impact compaction technique. We avoided the removal of 150,000 cubic meters of soil. So we're talking about significant volumes of material that can stay in place and doesn't need to be moved off site or sorted and rehandled. The entire process provided increased bearing capacity, supported all of the foundations, supported all of the heavily loaded floor slabs, racking loads, and significantly reduced or eliminated the settlement risk on the site. We'll likely show a number of structures on this presentation, but that's not to say that we aren't doing work in, like we said, storage tanks, infrastructure projects. This would be a great example from our team in Quebec of a roadway embankment. This was a new road that was being built to service a new residential development. It had quite a variable thickness of mixed fill soils underneath it, and dynamic compaction was used to densify the upper 7 meters, provide that strength, that stability, accept the load from the new embankment without having excessive settlements and any long-term concerns with settlement of those embankments and performance of that road. So I mentioned soil densification techniques. So this is when we're simply adding energy into the ground. Now we're going to chat a little bit about soil reinforcement techniques. So the difference here being is we're starting to use material inputs to modify the strength and stiffness parameters of the in situ soils. So the first one we'll talk about is what we call aggregate piers. This is sort of a catch-all term for a number of different installation methods. Again, we can go on the very deep side, with crane-based units that can treat over 30 meters of core soils, in allowing us to inject and compact that granular material deep into the soil profile. This is a great photo from one of our teams out on the West Coast. We have techniques that are generated are carried on more of a medium-sized sheet piling type rigs that are limited to about 15 meters of treatment depth. And then we have some tooling that can be easily adapted to available equipment for managing relatively shallow treatment depth. So the idea here, again, when we talk about things like carbon emissions, we talk about sustainability, cost, schedule. If you can bring the right piece of equipment to a job to treat the soils, you're going to have the lowest possible cost and the lowest possible impact to the environment. This is a pretty cool project that our team in Kelowna is working on. So it's a mixed-use development. It's a redevelopment of an existing boat club. So there's residential towers with podiums. There's a state-of-the-art boat storage, stacking facility, future clubhouse and restaurant right on the lake in Kelowna. Liquefiable soils were identified up to about 20 meters depth. And viral stone columns were used here to mitigate the liquefaction, improve the bearing capacity, and support the entire development. So again, a lot of value here without a ton of input. So we're not bringing a lot of steel to site. We're not bringing a lot of concrete to site. We are adding some additional granular material to backfill the subsidence, the craters from these compaction points. Able to densify that site though and remove that risk of liquefaction, remove the risk of settlement, and long-term and benefit the long-term performance of the site. We've seen this photo already. This is a mass timber building in Toronto. This particular site was a former industrial site. It had 5 meters or so of we say impacted fill and very high groundwater conditions. There was the initial plan was that obviously no one is going to dig the soil out. It would be incredibly cost prohibitive on a project like this. The site was looking at caissons. Caissons were going to need to extend to a significant depth. Menard was able to come in, proven through a competitive tender process with an aggregate pier system that reinforced that existing soil, gave a very high bearing capacity, limited the impact again of all of that trucking, of all of the material that have to come out from the caisson operation, and provided significant cost and schedule advantages to the project. So next we'll talk about controlled modulus columns. Again, there's a number of different ways that we install this. You'll see photos of rigs that are quite large, down to again techniques that can be hung off of excavators as small as about 35 tons. And this is when we start getting into concrete or grout. So just a quick animation here to help visualize the process. So use a displacement auger, a high torque drill rig, to squeeze our way through the compressible soils and into more competent material below. We then pump under a controlled limited pressure a concrete or grout product from the tip of the tooling and bring it up to the surface, where we can then cut it off at its required elevation. So set the height of those elements where they would then support a foundation or an embankment or a tank. Design methodology here. So these might look like piles. They might smell like a caisson. They probably taste like them as well. But this is not a pile type solution. And the big difference here is that when it comes to ground improvement, we're looking at a sharing of the stress between the existing soils and the reinforcement elements that have been installed. So we're saying the soil that's there, it's poor. It's not enough on its own to accept the new load, but it has some capacity. It's not worthless. Let's say we say so. Let's use it to its maximize its potential, and whatever it can't handle, let's balance that out with some reinforcement. So what you can see here is an example of a classic rigid inclusion, which you have a foundation on top of a load transfer platform, which is typically a granular mat that gets placed between the underside of the foundation and the top of the controlled modulus column elements, versus a deep foundation like caisson or driven pile, which is going to have a pile cap that puts 100% of the load into these pile elements, and that typically means you need to extend them a lot deeper than you would with controlled modulus columns. The game here is different. When you're dealing with deep foundations, the game is to say, let's get the maximum amount of capacity out of each element that we put in the ground, because there's such a high cost to each one. With ground improvement, it's saying, we don't need to go shooting for the moon on capacities. We want to put them in the ground as fast as we can, because that's what allows us to be more economical and offer a lot more value on A little bit on the installation. I think what's really neat about controlled modulus columns is that these are no vibration systems. So very much like caisson drilling, for example, we can install these very close to existing structures. We'll show some examples of installing these next to heritage buildings. Again, being fully displacement, you're not generating any drill spoils. That would then need to be managed or disposed of by the contractor. It's also relatively quiet. You sort of have the cycle of a concrete pump, the whine of a torque motor, and they get significant treatment depths. Because you're using a rotary drill rig, you have the ability to add extensions, Kelly bar extensions onto the unit, and be able to install to depths that are greater than the height of the equipment. So a lot of equipment that's vibratory driven, for example, will be limited by the height of the mast of that equipment in terms of the installation depth. That's not the case when you get into rotary drill rigs, and that allows us to tackle some soils that are below that sort of 15-16 meter depth where a lot of other techniques sort of tap out. Using drill rigs also gives us a pretty neat advantage from an engineering and quality control standpoint, because there's a lot of great data that can be pulled directly off of the sensors of this equipment. Allows us to get real-time monitoring of all of the drilling parameters, our torques, our rotations, our moving speeds, and all of this gets uploaded into the proprietary Menard Omnibox data acquisition system. And this is a very neat tool that we have that allows us to do a lot of project pre-planning, upload that into the rigs. Our operators know where they are, what element they are, which element number they're at, what the expected depths are. They can see the full response of all of the drilling to ensure that we're putting in the exact product that we're intending to. Of course, anytime you're using concrete, you're going to want to do compressive strength testing to ensure the mix that you ordered is what's being put in the ground. And you can also run full-scale static load testing on these to verify the results. I really like full-scale load testing with controlled modulus columns because it allows you to actually put load through the entire profile. When you perform load testing, static load testing on an aggregate pier, for example, if you have a limited concrete cap on top of that aggregate pier, maybe a 2-foot concrete cap, and you're trying to record its stiffness parameters, it works well to understand what the upper, maybe 3 meters, 2 or 3 meters of the soil looks like. But a lot of times we're treating soil that's significantly deeper, and there's a real gap in the understanding with load testing on aggregate piers below sort of the depth of influence of that load test. When you put load into a controlled modulus column, you're putting that load all the way through the profile, and you get very good confidence in what's being put in the ground and the long-term performance as well. So here'd be an example of one of the taller structures that we've done here in Canada. There's a 15-story mixed-use residential just down the road from me here in Hamilton. This site had, again, is impacted fills, some weak sands below that. There was a high water table. In fact, the site was designed such that it would be, half a meter or so above the long-term groundwater table to just stay out of that. And then there's some adjacent heritage structures, which you sort of see in relief in the background photo on the left. This entire development was supported on a raft on controlled modulus columns that extended through the fill, the weak soils to tag into the better material below. Nearly eliminated all of the dewatering. There was a little bit of dewatering needed to put in the elevator pit. Greatly minimized the shoring requirements by limiting only as much as was necessary to put the raft in, and avoided 15,000 cubic meters of removals, which of impacted soil would need to either go for treatment or to a landfill. It's also, it's a lot of fun to show, here's a 15-story residential building, here's a lot of big work and big equipment. Menard is across Canada doing projects of all sizes, right down to single-family residential homes. So this is a few photos of a number of projects throughout the country where we're managing these risks for residential developers. And the challenge is always the same. There's some sort of unsuitable soil condition. There's concerns about settlement, bearing capacity for these structures. And they're looking for options that avoid some of the cost and expense of some of the traditional methods that we've already talked about. Working with controlled modulus columns, we're able to reinforce the soil, give a reasonably high bearing capacity. Of course, these buildings aren't very heavy, but keep with the standard footings. So what that means is you can stay with relatively low complexity trench and pour foundations. You can keep with your typical contractor, that foundation contractor that you're used to working with, that may not have as much experience with pile caps and grade beams, some of the complexity in the tying of the rebar and the forming of those elements. We can also support the standard floor slab. So often these are, on the order of 100 millimeters or 4 inches thick on some granular. And this allows for future modification, which wouldn't be available if you had structural slabs on your site. So, someone occupies the home, now they want to, put in a new washroom in their basement, or they, for some reason they need to get below the slab. It's a relatively easy process to chip that slab up, install the surfacing, and then reinstall the slab without having performance issues. I guess back to some big projects. This is an Amazon warehouse with our team in Calgary. This was a very cool project, very aggressive construction schedule. 4-level, 65,000 square meter distribution warehouse. So significantly big. You can see in the bottom right photo, some of the foundations here. And the grid that was being done. Menard started the project with control modulus column, carried along. The excavating contractor was digging up right behind us. The forming contractor was right behind him. Everyone chased themselves around the site, was able to offer a lot of value. This particular job had been originally designed for an aggregate pier solution. Menard was able to work with the winning contractor on a value engineering using controlled modulus columns, which saved a considerable amount of cost and was also faster to construct. And now going back to sort of the small side, another warehouse, but this one was under construction. Identified a pocket of saturated fill. We're sort of back to one of these gravel pit redevelopment sites. And there was an area of the site that where some very saturated silts and clays had been dumped. This had an impact on the site of only about 100 meters of wall. Foundations for most of the building were already in. Menard got the call and said, is there something we can do to avoid digging this all out, avoid going to some sort of piling system? They did look at helical piles on the job, but ultimately the control modulus column system installed with very small equipment was able to maintain the foundation design. So no change to the rebar that they had ordered, no change to to the forming, and the entire works, all the concreting was actually completed in about 3 hours. So let's talk about some of the proven benefits. We've mentioned some of these already, but we'll just give a bit of an overview of sort of the impact of working with ground improvement. I think the main one here is to significantly reduce soil handling and disposal. Anytime you're dealing with moving earth, there's cost associated, there's time associated, there's risk associated. You're also now bringing that through communities. The trucking of that material is generating a lot of carbon emissions. Anytime you can reduce the amount of soil that you need to move, it's a win for everybody. This also allows you to greatly reduce the overall project cost. We've shown a number of examples of that. Maintaining standard footing construction. Again, if this is on that small residential job, allowing you to maintain that rapid, trench and pour, on larger projects. If you're getting into, even if it's a raft foundation, you have no elements that are coming up into that raft that are creating perforations. It's a very simple process. When your contractor comes on site, it's like they had good ground to begin with, and they're just building, removing all that risk and uncertainty that's also often associated with the soil conditions. Again, if you're going to use systems that are faster to construct, that's going to have an impact to your project schedule, a positive impact, but also removing the risk from that site has a positive impact to your schedule as well, because you're not going into construction and finding unknowns, finding challenges that now need to be managed, and putting delays in your schedule. Schedule can drive a lot of projects, especially once they get going. There's a very specific sequence of events that needs to happen to meet the timelines, and any sort of hiccup along the way can be really detrimental to the overall success. Ground improvement removes that risk and lets you get on with your construction. And of course, major benefit to project sustainability. So often we're seeing 1/10, 1/20th the carbon emission of earthworks operations, piling. This allows us to just be better with how we do construction, I think. And it's great to see that there's a lot of interest in this these days, and I think it's for very good reason. And we're quite happy to be a part of the process of tackling some of the challenges with carbon emissions and overall project sustainability. So we'll go to a couple questions. I've just got a few here from the Q&A. Again, like I said, we will try to summarize some of these and return with some direct questions at a later date. The first one I have here is, what is the impact on existing structural foundation with dynamic compaction? So that's a great question. So you have an existing building and you want to look at doing dynamic compaction, maybe for a future expansion or an existing building nearby. Depending on the technique and the energy that you're using, there are certain offsets that should be maintained. With rapid impact compaction, that might look like 3 to 5 meters. With dynamic compaction, that might widen out a little bit more, and with vibro, you are able to get actually surprisingly close. That being said, what Menard does and what's always carried in our proposal on these projects is to do precondition surveys of any buildings that are within about 50 meters of where the compaction work will be taking place. We also do on-site vibration monitoring through a third party to ensure that we're not exceeding acceptable thresholds. So thank you for that question. The next one is, can you dynamically compact uncontrolled clay fill soils? Great question. The answer is maybe. If you're going to use a technique like rapid impact compaction, for example, where you're going to strike the ground at a rate of about 40 times per minute, you run the risk in clays that you'll generate poor water pressure, and you can start making more of a mess than providing a lot of benefit. That being said, if you have a uncontrolled clay fill that's in a dry state, and you use a dynamic compaction method, so with a much larger tamper foot, a much lower rate, a higher energy at lower frequency, we've achieved very good results in clay fill soils. The next question that came through here is, what impact does ground improvement techniques have on the soil/structures around it? Is there a limit to how far away existing structures need to be for the ground improvement technology? So we mentioned about the dynamic compaction and rapid impact compaction. When it comes to aggregate-based systems, we can get quite close to existing buildings. There's often an offset of maybe 1.5 to 3 meters, depending on the technique and the energy. And as we mentioned with controlled modulus columns, which I think is a major benefit of that system, is that it's a zero vibration installation method. It allows you to get very close to existing structures, and we showed some photos and examples. Next one here is, can you reliably assess the settlement characteristics of a range of soils treated by the various compaction techniques? The architects and structural engineers usually want a very restricted maximum settlement. So absolutely, this is not geotechnical wizardry. This is geomechanics. The design methodologies that are used have been proven here in Canada, but also globally. Many of them come from codes that have been validated by authorities. With some of these newer techniques like controlled modulus columns, for example, they've been heavily vetted and validated by European authorities, and we follow the good guidance that they've generated here in Canada. So yes, and then the other aspect to that is that it's one thing to run a design as everyone knows, it's another thing of what you get on site. So we're always checking and verifying the results. So if it's a dynamic compaction project, for example, we may, I shouldn't say may, we will go back and do a post-compaction investigation of the soils. That could be using standard geotechnical investigation methods, but more often it's again using the Menard pressure meter to allow us to accurately assess what the increase in soil capacity was. When it comes to reinforcement techniques, so whether it's aggregate piers or controlled modulus columns, full-scale static load testing or modulus load testing, you can also do post-installation verification using pressure meter or CPT in between compaction points for things like the project we showed in Kelowna for the boathouse to verify that the liquefaction potential has been reduced. Next question here is, what is the average spacing of the rigid inclusions? So that's a great question. Again, with a lot of this, it's going to depend. Like we said, the existing soil has some capacity. So depending on the capacity of that soil is going to enlarge, and the amount of load that's being applied is going to largely dictate what your spacing is. It's typical to not install them closer than about 3 to 4 times the diameter of the elements that you're putting in. There are ways of managing that if you need to go a little bit tighter, but generally speaking, that's a good starting point. And then there are sort of certain limits. You may not, in certain soil profiles, want to space these wider than about 3 or 3.5 meters. Grid underneath, say, a floor slab or along a lightly loaded foundation wall. Question here is, what are the negatives of soil compaction? So done right, there are no negatives. It's all a net benefit. I would say probably some of the potential challenges that could arise. Again, we mentioned about not being able to always 100% know what the soil conditions are below a property. You can get a lot of borehole information, you can get a lot of test pit information, and you can get to site and you can identify something that's not an area of the site that maybe not well represented by the information that you have. That is easily identified during the compaction process. You quite simply see that the soils aren't compacting, and then those areas can be delineated. The poor uncompactable soil can be removed, replaced with a granular, and then Menard typically compacts that in place without additional charge. And next is, can we use recycled concrete inside the aggregate piers? The question, the answer is again maybe. It depends on the installation method and what sort of recycled concrete you're looking for. Or looking to use. So fresh crushed recycled concrete. So the material that gets brought back to batch plants and gets crushed is a great material for a lot of applications. When you get into recycled materials that may have higher contents of things like asphalt or bitumen, that can challenge the some of what you're trying to do when you're trying to add additional energy into the soil, and now you're dealing with asphalt particles. That can be a challenge. Next one is, could you elaborate on water pumping or groundwater management during dynamic or rapid impact compaction efforts? Yeah, absolutely. So water pumping is essentially as you're working the soil, the moisture, the groundwater with under its capillary action you can drive up the pore water pressure, and you can bring that water to the surface, and that could have a negative impact on what you're trying to accomplish. One of the things that challenges that is the drainage of the soil. So if you have poor drainage, you have a higher risk of pumping. And the other would be the technique itself. So as we mentioned, techniques like dynamic compaction using larger tamper foots, maybe it's a 15-ton, 3-meter wide tamper foot being dropped 15 meters from a crane at a rate of once a minute or so, versus rapid impact compaction, which uses a much higher frequency, lower energy, might dictate the end result. So the higher the frequency, that you're using, the more risk you have on your site of generating that excess soil pressure and creating concerns more than doing good when you're in some of these sort of mixed fill soils. Sands are very easy to treat. There's a lot of different ways you can manage sands. But you need to be a little bit more careful as your fines contents increases, so as your silts and your sands start to elevate. Next question is, when you're compacting, do you need to bring in new soil? So that's a great question, and it really comes down to the needs of the project. Oftentimes, we are simply backblading with the existing material that's there. So filling in the craters with material borrowed from the site, if it's of a suitable quality rather. There are techniques, and again, we didn't have a chance to get into every sort of technique available. Dynamic compaction sort of has this little sister or little brother called dynamic replacement, where you are bringing in new granular materials, and as you're compacting the site, you're creating these craters. You can fill it with new granular, recompact it to get good results in profiles that may not respond well to just densification on its own. How can you prevent the heave in the soil using CMC? What is the maximum load that can be applied on a controlled modules column? So heave is an interesting topic. So there's a couple things that generate heave on a site. It's often a function of how closely together you space these elements. And then the actual nature of the soil itself. So if you're in a saturated silts, for example, silts and clays, you may be much more concerned about heave on your site because they're not really looking to compress or densify. That the moisture, the saturation level is such that when you sort of squeeze your way into that site, it's kind of, it wants to go somewhere, and sometimes the easiest way for it to go is up. That being said, heave with controlled modules columns is much less of an issue than maybe heave with aggregate pier systems, particularly in those saturated silts. With aggregate piers, you're really working the soil, whether it's with a vibro or with a vertical ramming process. You're stuffing a lot of gravel in the ground. You're trying to compress that soil, and you can really drive a lot of vertical movement in the site when you're in sort of saturated silts, particularly. There are approximation calculations that can be done to estimate how much heave will be generated from these processes, and you can use that number to get a good sense of maybe where you should work in soil profile. So you might be on a site that might be a little bit low lying. Maybe you're not then so concerned about heave because you have to raise the grade anyways, so maybe it was a little bit of a benefit. But if you're on a site where you've cut to an elevation and you want to sort of stay there with very, very minimal rework, you want to know then if you have a risk of heave, or if maybe you should lower that working elevation a little bit to allow you to bring in a couple trucks of gravel after and just re-level out the site. Next question is one about peat soils. So highly organic soil material. It said, are any options for peat where we want to construct a building, or does it have to be removed and replaced with engineered fill before compaction? So you're not going to compact a peat. There are great methods for it, and namely, I would say when you get into concrete-based systems like controlled modules columns. Peat in itself represents risk. It represents risk of future settlement. Primarily, it also represents risk of as it degrades. If you use a system like an aggregate pier, for example, which relies entirely on the soil that surrounds it to generate capacity, if you try to work that into a peat soil, even if you generate a little bit of capacity initially, as that degrades, you'd be very concerned that through that peat zone, you're going to lose that confinement and that strength over time. Controlled modules columns, on the other hand, they have their own structural capacity. They're a concrete element in the ground, so you can do a lot, and depending on where the peat is in the profile of taking the foundation stress or the new stress, having it collect into the controlled modules column, extend its way through the organic soils and then dissipate into better material below. Next question here, which I think we mentioned already, but this is how is the soil after improvement evaluated to check if it is competent enough? So again, if it's a dynamic compaction process, we're going to do a post-installation GTEC investigation. Could be using a pressure meter system, or other methods to verify that the densities have been achieved. Ultimately, Menard has a team of ground improvement experts, again, coast to coast. We are taking on full responsibility and liability for any work that we do. We are, I would argue, most concerned about the performance of the sites that we get involved in. And we do a lot on our end to ensure that the intentions, the design intent has been achieved. Again, when you get into systems like controlled modulus columns, you have all the great data that you can pull off of the drill rigs in terms of the real-time monitoring being uploaded to the Omnibox system, which allows us in real time, like from the office here, I can watch as elements are being installed, really anywhere in the world, which is pretty cool. So that engineering review being a big part of it. On-site quality control being another big part, and then load testing as well. Next question is, so for CMCs, what is the minimum distance between each CMC? So generally speaking, like we said, it's on the order of about 3 to 4 times the diameter, depending on installation method and soil conditions. Do you use pile caps to connect the CMC to the footing? If no, what do you use? So again, the goal here, the game here, is to get you away from pile caps and grade beams. You certainly could use them. There's nothing stopping you from using them, but they are more expensive and more complex to construct. We are generally supporting high capacity strip and spread footings. So again, like you had good ground to begin with. Next one is, for loose soil on a rail embankment, 2-to-1 slope, what would be the best option for compacting the slope without impacting railway operations? I think it would be very, very dependent on what the soil conditions are below. If we're right next to an existing rail, I think we'd have to look at how close it would be to understand whether a compaction option is the best option. Certainly a number of project examples using controlled modulus columns, or we actually have another technique, sort of a play on that, which is bi-modulus columns, where we use a concrete-based ground improvement, but we finish the top with more of an aggregate pier that have been used right next to railways. And those techniques can often be very effective and don't result in sort of any sort of major subsidence or movement of the existing rail. I'm going to take one more question here. It says, so I'm asking again about compaction on clay soil with high moisture content, such as highly plastic soil and collapsible soil. I thought compaction would remold the soil more than improving, and I would go with preloading instead of compaction or even rigid conclusions. And I would 100% agree with that. And when you are in a high moisture condition, compressible soil, there's a lot of value that can be done with preloading. We didn't have the time to talk about it today, but preloading with techniques like wick drains, or in very sort of niche environments like a Menard vacuum, it can be a very cost-effective way of accelerating that process of allowing, essentially, with the preload, is placing load on top of the soils to drive the settlement out ahead of construction. That settlement takes some time. If you put drainage elements in the ground, you can accelerate that time. And perhaps I wasn't clear earlier, but I would in no way recommend using dynamic compaction on high moisture content clay. If you're in a dry state, in a fill, there's good value that can be achieved. And then we'll do one more here that just came in and say, any advantage on high-rise buildings which may encounter compression on one side and tension on the other side due to wind loads? So tensile capacities or uplift capacity is an interesting one. I guess the first thing I would say is, while we're obviously very passionate about the work that we do, we're very passionate about ground improvement. Each technique, each combination of techniques, it's not a catch-all solution. It's not always a silver bullet. There's a reason why there's a lot of other foundation techniques out there. You can generate uplift capacity with things like aggregate piers and controlled modulus columns. Generally speaking, I would say if there's a significant uplift demand, you want to look at either oversizing the foundations, adding some weight, putting them lower in the ground to manage it without trying to use the ground improvement to develop any uplift capacity. Or if it's in an extreme case, you may be looking at something like a helical pot or some sort of anchor micropile, something like that. Okay, so great. I think we will wrap that up here. Thank you so much for your questions and taking the time to join us today. I will quickly present our upcoming webinars. So for those of you that may have yourself or may have colleagues more interested in a French language version of this webinar, there is one being held on March 23rd. We also have in the series coming up, we'll be talking about mines and dams, residential buildings, topics specific to warehouses, and as well as industrial buildings. So I hope you can join us for that. I do hope that we've given you a little bit more insight into what sort of methods are available here in Canada, some of the work that we're doing. And as I mentioned earlier, if you have any questions at all, if you'd like to understand if ground improvement might be beneficial to your project, please don't hesitate to reach out to your local office. You know, like I said, we're here for you from coast to coast. Contact details all on the website, menardcanada.ca. And with that, I wish everyone a great day and hope to see you on the next one. All the best.